Hello everyone, my name is Shagur Bishwas and today I will present a review of the ISCA 2019 paper, CoNDA, Efficient Cache Coherence Support for Near-Data Accelerators. Before talking about CoNDA, let's review cache coherence. In multi-core processors, each core has private caches. If multiple caches hold the same memory block and one core writes to it, we must ensure other cores do not read stale data. This is the cache coherence problem. All cores should see a consistent sequence of writes for every memory location. The goal is to ensure correctness while allowing caching for performance. Now, MESI protocol. It is one widely used coherence protocol. In MESI, M stands for modified, E exclusive, S for shared, and I for invalid. State transitions are triggered by local reads, writes, bus events such as bus read X, bus upgrade, invalidate, etc. The diagram in my slide shows the processor-initiated transitions clearly. Okay, now directory-based coherence. Snooping does not scale because broadcasts grow with the number of cores. That's why modern machines use directory-based coherence, which we learned in chapter 10. The directory tracks the global state of each block, where U stands for uncached, S for shared, EM for exclusive and modified, and shared vector indicating which cores have a copy. Now, in typical transactions, a core sends a read or readx request to the directory. Directory checks state and sharers. It sends data or invalidation messages accordingly. And directory coherence scales better but increases message hops and latency. Now, memory consistency and ordering. Uh, Coherence covers single memory locations, and consistency defines global order of memory operations across threads. Under sequential consistency, there must exist a total order of all memory operations. Now, each core's program order must appear in that global order. CoNDA uses sequential consistency as the base model for explaining optimistic ND execution and commit ordering. Why conventional coherence is a problem for NDS? So now we are transitioning into the CoNDA paper. NDS are small compute engines which are located close to memory, that is inside 3D stacked DRAM. They are ideal for memory-intensive workloads such as graph analytics. But integrating NDS into a CPU's coherence protocol has a major problem. NDS often have very high cache miss rates due to their poor locality. Now, treating the NDA as a full messy participant causes massive coherence traffic, even often off-chip, which eliminates the benefit of near memory processing. So, conventional CPU designed coherence protocols do not fit NDA behaviors well. Now, there are some existing NDA coherence approaches. So, this paper compares three approaches. First of all, non-cacheable region. So in this case, the CPU bypasses the caches entirely for NDA data. You can see in these diagrams that for this approach, the NDA is going to take the data from the DRAM and the CPU won't cache any data at all. So every time it needs a data, it will get it from the DRAM. And it's definitely going to slow down the whole process by a lot. The second one is the coarse-grained coherence. Now, in this case, what the NDA does, it acquires a lock over the data it's going to use. So actually, it locks the whole data in the DRAM. So the CPU has to flash the whole region, and then the NDA locks it and uses it, and then unlocks it. After that, CPU can use this data again. But as we can anticipate that due to this kind of approaches, there will be a lot of flashes, unnecessary flashes from the CPU. And the last one is the fine-grained MESI. So now India fully participates in MESI protocol, but this causes huge number of coherence messages. So we can say that none of these approaches are good for NDA. Now near data accelerators baseline architecture. This slide explains the baseline architecture of the paper is working with. The system consists of a multi-core CPU that uses directory-based MESI for coherence and a 3D stacked memory structure, which is similar to HMC. That includes a logic layer where several near-data accelerators operate. Now, these NDS run memory-intensive parts of the workload that are offloaded by CPU threads. And importantly, the CPU and the NDS share the same data structures in memory, such as graphs or tables. Because of this shared memory interaction, CoNDA's goal is to maintain a correct, coherent view of memory, but to do so while minimizing unnecessary coherence traffic so that it gets the benefits of near data processing are preserved. Now, application analysis. So the authors analyze the real CPU NDA workloads. They find that CPU often reads or writes NDA data. True simultaneous conflicting accesses are rare. Most coherence messages are unnecessary. So this suggests room for optimistic coherence. So don't pay the full coherence cost unless there is actually a conflict. The key insight is most coherence traffic is unnecessary and conflicts are rare. So instead of sending coherence messages for every NDA access, let the NDA run optimistically and only handle coherence afterwards if necessary. So this is the core idea behind CoNDA. Now, the CoNDA high-level idea. In CoNDA, NDA executes assuming it owns the data. Then NDA logs its read or write sets. CPU logs writes to NDA region. At chunk end, it compares the signatures. If there is no conflict, it will commit. But if there is a conflict, there will be a rollback and re-execute with coherence actions. So execution model under sequential consistency. Under sequential consistency, CoNDA commits an entire NDA chunk atomically at its commit point. Now, CPU operations inside that window are ordered before or after NDA commits. If the NDA read a value the CPU modified, rollback ensures sequential consistency is preserved. Thus, CoNDA gives correct SC behavior while allowing optimistic execution. There are four main access combinations: CPU write plus NDA read, NDA write plus CPU read, CPU write plus NDA write, and NDA write plus NDA read. Now, in these four cases, only case one, that is CPU write plus NDA read, triggers re-execution. This is the rare in real world workloads. Now, tracking memory access with signatures. NDA maintains Bloom filter-based signature sets that are NDA read set, NDA write set, and CPU write set. Bloom filters introduce false positives but never false negatives. So false positives only cause occasional unnecessary rollbacks but no incorrect behavior. This allows compact logging of large access sets. Now, CoNDA architecture overview. Now, NDA begin starts a chunk. Then there is optimistic execution. That means this NDA starts executing its operations optimistically. And then it tracks the signatures, like the reads or write signature. It tracks both the signatures from NDA read or write and CPU writes. In the coherence resolution section, it actually compares the signatures from NDA and CPU. If there is no conflict, it will commit the writes. But if there is conflict, it will roll back and re-execute the exact part of the operations that needs to be re-executed or impacted by the CPU writes and re-execute only that part of the operation. So this is the high-level architecture overview of CoNDA. Now let's go to the results. The key results are up to 20% performance speed up over best existing NDI schemes, up to 18% reduction in DRAM energy. It comes within 10% of an ideal coherence baseline. It gains increase for larger datasets. So this clearly shows CoNDA significantly reduces unnecessary coherence overheads. Now, what I understood better after reading CoNDA. Reading CoNDA paper helped me solidify the following concepts like the cost and the complexity of directory-based coherence, the distinction between coherence versus consistency, especially using sequential uh, uh, consistency, sequential consistencies in optimistic models, why coarse-grained and fine-grained coherence both fails for NDS, how different hardware mechanisms, that is MESI, directory, interact in modern heterogeneous systems. So this paper tied together many concepts from the course, I would say. Now some strengths of CoNDA. Excellent match to NDA behavior, that is low conflict rate and optimistic execution is ideal. CoNDA reduces coherence traffic significantly. CoNDA requires only small hardware changes, that is Bloom filters and per word bits. It clear correctness argument under sequential consistency. This performance scales with data size. So these strengths make CoNDA realistic and impactful for future near memory accelerators. Now, CoNDA also has some weaknesses. CoNDA depends heavily on low conflict frequency, so some workloads may not fit it. Frequent rollbacks could undermine performance in edge cases. Bloom filter false positives cause unnecessary re-executions. And this paper needed to discuss more on system-wide issues like multiple NDAs, virtual memory corner cases, security concerns, and OS interactions. Thank you. This was the end of this presentation.